We're going to start by talking about quadratic surfaces. So we've seen so far surfaces in 3D space that are given by equations of the first degree. These are planes. Things become a little more interesting if we again want the surface to be defined by a polynomial equation, but we allow the degree to go up to 2. And we have already seen a kind of such surface. That would be the sphere. So if we consider the sphere centered at the point ABC with radius r, then that is given by the equation x minus a squared plus y minus b squared plus z minus c squared is equal to r squared. Now, to see another type of surface, it's interesting to ask what happens if we get rid of one of these terms on the left of the equation. Meaning, let's say that we consider x minus a squared plus y minus b squared equals to r squared. And we still insist that we are in 3 dimensions, because somebody might see this and say, oh, you know what, that's in 2 dimensions, it's a circle. Well, if we are in 3 dimensions, then the fact that it's a circle in 2 dimensions means that on the xy plane, it will be a circle. But then if you think about it, that also means that on any plane which is parallel to the xy plane, you will have the same thing. And if you stack up all the circles, one over the other, then eventually we get a cylinder. A cylinder centered at AB, 0 with radius r. And if we remove not the z minus c squared term, but let's say the x minus a squared term, then we're going to get a cylinder whose axis of symmetry, that has an axis of symmetry, which is parallel to the x-axis. So this is the equation of a cylinder. And what is interesting from what we just mentioned was that we can think of the cylinder as made up by circles that we stack up. And this kind of thinking can be used in a similar situation. So when we have a quadratic surface, we might ask, what is its intersection with different planes, and try to piece together what the surface will look like just by knowing what the intersections of the surface with a plane will look like. In particular, if we take the intersection with the xy plane, the xy plane has equation z equals 0, and then we obtain the so-called xy plane, xy trace, I'm sorry. If we take the intersection with the y plane, with the xz plane, which is defined by the equation y equals 0, then we get the exit trace. And finally, if we take the intersection with the yz plane, which is defined by the equation x equals 0, then we get the yz trace. And of course, if we want to enhance our understanding, we can also take the intersection with planes that are parallel to these planes. So let's give an example. So let's consider a quadratic surface given by z is equal to x squared plus y squared. Let's try to understand what it would look like geometrically. So we sketch the coordinate system in 3D. And then if we take the xy trace, which is obtained by z equals 0, so for this one here, the xy trace is not all that interesting. It's just a point. It's a point 0, 0, 0, the origin. So that doesn't give us too much. But if we consider the xz trace, so the xz trace gives us the intersection of the surface with a plane which is spanned by the x-axis and the z-axis. That is obtained for y equals 0. Then we're going to get z is equal to x squared. And z equals x squared is a parabola on that plane. Also, the yz trace, which is obtained by setting x equals to 0, will be z is equal to y squared, which is another parabola. And eventually we see that what we get is this parabolic cone, or sometimes we will call this just simply a paraboloid. And for example, to enhance a little bit our understanding of this, we could have taken the intersections with planes of the form z equals a, which would of course have produced a circle that looks like x squared plus y squared is equal to square root of a all squared. And that means it's a circle of radius square root of a. And this means that all the intersections of this surface with horizontal planes, as long as those horizontal planes are above the xy plane, are going to be circles like this. So we can have now a variety of surfaces. We can play with different configurations. And for example, we can get to hyperboloids. So for hyperboloids, what we really need is an equation of the second degree where we have at least two different, we have both plus and minuses. So let's start with something like this. So if we consider this, then we have a very interesting situation, because if we take the xy trace, which is obtained for z equals 0, we get x squared plus y squared is equal to 1. So that's the unit circle on the xy plane. If on the other hand, we take the yz trace, which is obtained for x equals 0, then we get y squared minus z squared is equal to 1, which is a sort of, which is a parabola, not sort of parabola, it is a parabola. And eventually, if we take the xz trace, we will have another parabola. And that should complete the picture of this paraboloid. The interesting thing is that this paraboloid is, as we say, connected. It comes in one piece. And we can have paraboloids that have two pieces, two sheets, as we say. So this is a one sheet paraboloid. I'm sorry, hyperboloid. So the question is, how can we play with, how can we obtain an equation for a two-sheeted one? And the answer is, for example, put a negative number on the other side. So consider the equation x squared plus y squared minus z squared is equal to -1. What will happen then is, if you think about it, and in this case, it might be a good idea, as it was before actually, to realize that these hyperboloids are obtained by stacking up circles of varying radii. So I'm talking about all these circles. The radii go up as you go higher and higher, or lower and lower. And here, if you transfer over the z to the other side, you will realize that for certain z's, this number is negative. In particular, for z in absolute value less than 1, this quantity is negative. What does that mean? That means that the intersection, since you have something non-negative on the other side being equal to something negative, that means that there will be no points, which means that the intersection of whatever surface is represented by this with our plane for z in absolute value less, for planes that are between the plane z equals 1 and z -1 are going to be empty. And basically what it's going to look like is going to be a paraboloid with two sheets. So this is going to be a two-sheeted paraboloid. In general, in our course, we're going to look at this kind of surfaces. So we can have some other interesting situations that we're not going to get into. And at this point, we're going to start talking about vector valued functions. So a vector valued function is a function whose outputs are vectors. And in our case, we'll be interested in functions of one variable. And you can have either dimension 2 or dimension 3. So t squared minus 3, 3 plus cosine t. And let's write down a one with 3 coordinates, like so. What is kind of interesting here is that we view this as motions. So at time t, we consider the point that is the terminating point of the corresponding position vector. Again, recall that when we talk about position vector, we actually think of them as originating at 0, 0. So for time t, this gives us a certain point. And if we connect all these points together, then we get a curve. That curve will be called the trajectory of the vector valued function. Now, as with any type of function, we can have domains of definition, we can add them up, we can subtract them, simply because we can add up and subtract vectors. And obviously, we can differentiate them. So take the second function, for example, then its derivative will be negative sine t, cosine t, comma 1. In fact, if we consider them as motions, then the initial function, we can think of it as the position function of the motion. Its derivative, which could be also denoted by v of t, is the velocity function. The length of the magnitude of the velocity, which is going to be denoted by just the letter v, is going to be the speed. And finally, if you take the second derivative, then you get the acceleration. So the example that I just gave you, r of t is equal to cosine t, comma sine t, comma t, has as its trajectory a helix. The velocity is negative sine t, cosine t, comma 1. The speed is actually constant in this case. It's the magnitude of this, which is square root of 2. And the acceleration is negative cosine t, negative sine t, comma 0. What is kind of interesting here is to ask the opposite question, which is, if they give us a curve, can we find the vector valued function whose trajectory is the given curve? That is called parameterization of the given curve. And it's a good idea to know how to parameterize some very important curves. For example, a straight line. We have already seen how to parameterize a straight line. If you know a direction vector and a point on the line, then the vector valued function that you get, that traverses that line, if you will, is the vectorization of the point plus t times ABC. If we have a circle in 2 dimensions, for example, the unit circle is parameterized by cosine t sine t. And here, if you want just one rotation, you can specify that t is between 0 and 2 pi. If you want more, you can adjust always the parameter depending on how many rotations you want. Also, if you have a more general circle, let's say that it's centered at AB and it has radius r, then the parameterization is r of t is equal to a plus r cosine t, b plus r sine t. What else? Let's parameterize an ellipse. The ellipse x squared over a squared plus y squared over b squared is equal to 1. You just need to tweak a little the parameterization of the circle, and you will get r of t equals to a cosine t, comma p sine t. And again, t is between 0 and 2 pi. I should mention here that we also have the line that goes through 2 points. We gave a simple formula for it. The formula is r of t is equal to 1 minus t, x naught, y naught, c naught, plus t times x1, y1, c1. An important general parameterization that we should all know is that of the graph of a function. So let's say that you have the graph of a function from the point A to the point B. Then this can be parameterized by t comma f of t. That's how you generate the points on a graph for t between A and B. We could give more, but these are the most important ones. And continuing on vector valued functions, it would be useful to say that we can do calculus with them. So we already said how to find their derivatives. If we have a vector valued function, then we can find an indefinite integral or a definite integral for it. So let's say that f of t is t comma t squared comma t cubed. Then its indefinite integral is going to be t over 2, t cubed over 3, t to the 4th over 4. And here, you might argue, well, where's the c? Usually when we find indefinite integrals, we put a c. Here, you would normally have to put c1, c2, c3, because the constant on one coordinate should not have to be related to a constant on the other coordinate, but you can pack all the constants in one vector and just call it c. On the other hand, if you need to do a definite integration, then this goes the indefinite integral. So if we plug in 0 and 1 and subtract, we will get 1/2, excuse me, 1/3, and 1/4. And that will be our vector. We have actually some very interesting formulas. If we look at some of the operations between vectors, both formulas that I'm going to give you are generalizations of the product rule, if you will. So the first one is if you have two vector valued functions and you take their dot product, and then you want to take the derivative of this, then that will be the derivative of the first dot the second plus the first dot the derivative of the second. If you play with cross products, then it's going to be a very similar formula. Oops, derivative here. And there's one very, very remarkable property that we should mention here. And that's the following. If you have a vector valued function with constant magnitude, then its velocity, meaning the derivative, is perpendicular to it. Let's actually try to justify this. It's kind of interesting, and it's a nice review of some of the concepts that we have seen so far. So if we know that the magnitude of a vector valued function is constant, then that means that the square will be constant. Yes, but the square of the magnitude is what? It's the dot square. And so if we take the derivative, we'll get 0, which means that the derivative dot the function plus the function dot the derivative is 0. That means that twice the derivative times the function dot the function is 0, since the dot product is symmetric, which means that f prime of t dot f of t is 0, which means that the two vectors are orthogonal. There are a few more things that we should look at in the context of vector valued functions that we're going to just leave them for our next lecture. Thanks for watching.